Apologies in advance, I'll be wearing the mask during the talk given recent events. I hope everybody can still understand what I'm saying. Okay, great. So I'm here to talk about QUIC, and I named this talk a deep dive because we'll not do a lot of why is QUIC better than TCP and how does QUIC achieve this, but we'll dive into some of the important or some of the interesting things in the specification. I'll do a very quick overview at the beginning, so everybody's up to speed. QUIC is a new transport protocol. It's defined in a range of RFCs, starting with 8999 to RFC 9002. And the publication of the RFC describing HTTP3 is still outstanding, will happen later this year. I myself, I've been part of the IETF QUIC working group since the beginning in late 2016, and I've followed all the process and participated in all the discussions that led up to these RFCs. At the moment, there are around 15 QUIC implementations that I'm aware of. Most of them are open source, and almost all of them are running in user space. As far as I know, there's only a single QUIC implementation that can run both in user space and in the kernel. So QUIC is a replacement or an addition to TCP. It is based on UDP, and it's basically better in every sense than TCP. However, it's blocked on certain networks, so you can't like completely replace TCP as of today. QUIC offers native stream multiplexing at the transport layer, and these streams are behave. You can think of it like as independent connections, so there's no blocking between writes on one stream and writes on another stream. QUIC is always secure. TLS 1.3 is baked into the protocol, which means you get connection establishment within one handshake to a server that you've never talked before. And if you've talked to the server before recently, you can do a 0 RTT handshake and send application data right away. QUIC offers advanced loss detection, loss recovery, and congestion control algorithms. So you can expect some speed up compared to TCP in that regard as well. And QUIC supports connection migration, which means, for example, if you're on your phone and you're currently on Wi-Fi, but you're walking away from your Wi-Fi, you can migrate the QUIC connection that you have to your cellular connection without losing all the state or the streams that you have on that connection. So that's all that I have for the basics. And first topic I would like to talk about is how would you do load balancing with QUIC? So this is a fairly typical setup that you would have. You have a load balancer on the left that's receiving all your traffic from the network. Could be HTTP requests, HTTP3 requests. And you have a bunch of backend servers, or at least servers that are intended to terminate the TLS connection, terminate the QUIC connection, and then probably pass this on to a separate set of backend servers. So in the TCP world, this is pretty easy because a TCP connection is defined by the two endpoints, IP address and port on the one side and the other side. But in QUIC, that doesn't hold anymore, right? We have connection migration. So we can't just look at the IP address and then do some kind of hashing to assign a server. Instead, what QUIC does is it uses connection IDs. And connection IDs are kind of a misnomer because one connection doesn't have a single connection ID. It has at least two connection IDs because both client and server choose their own connection ID because both client and server could potentially be behind a load balancer, right? And each load balancer has their own configuration and needs to make sure that the connection is routed deterministically. And in practice, the connection doesn't only have two connection IDs, but connection IDs change over the lifetime of a connection. nodes will just randomly roll over to new connection IDs, and when they do a connection migration, they will also change the connection ID to break the linkability between the old path and the new path. So this increases the privacy when there's somebody watching the packets that go along the network. So how exactly does this work? I've here a diagram of QUIC packets, and there are two QUIC packet types. The first one is the long header packet. The long header packet is, as the name says, pretty long. It is only used during the handshake. So we don't really care that it's that long and that we are wasting a bunch of bytes, because in every single QUIC connection we send maybe like 10 or 20 of these packets, so it doesn't really matter. Long header packet starts with a 1 in the first bit. Then we have a QUIC version, and for some reason people thought that we need 32 bits of QUIC versions. So we have like 4 billion different QUIC versions that we could potentially use someday. So far we have used one of them. The next field is the destination connection ID. So this is the connection ID that the receiver of the packet will use on their load balancing infrastructure to route the packet. And then after that, there's the source connection ID. So when the client sends the first packet, it will fill out the source connection ID. It knows about its own infrastructure and how the connection ID needs to be shaped to be routed correctly. It doesn't know anything about the server yet. So it will just fill in like random bytes in the destination connection ID. And then when the server replies to this packet, it will use the client source connection ID as the destination, and it will then give the client a new connection ID. It will use this new connection ID that is then consistent with the load balancing infrastructure that the server is using. So once the handshake is done, both nodes switch to the short header packets, which is here below. And you can see the short header packet is really short. It starts with 1 byte, which has the type in it. The first bit is 0. It has then some like version-specific use of the following bits. And then there's only the destination connection ID. And you always use the destination connection ID that your peer gave you. So it makes it through their load balancing infrastructure. The funny thing here is you can see in the long header packet we had a field for the destination connection ID length. Maybe it doesn't really show very well on the projector here. So there's a length field for the destination connection ID. Connection IDs can be anywhere from 0 to, in the general case, 255 bytes. Although in practice you probably don't want to use that long connection IDs. In the short header, there's no length field. So the peer will remember the length. So we are saving that 1 byte for the length field there. This also has the nice property that an on-path observer that receives 1 QUIC packet can tell this part is the connection ID and this part is now the packet payload. It's just opaque bytes for them. Until, of course, they observe multiple packets, then they can probably infer which part is the connection ID. Okay, so much for load balancing. Another thing that I find quite interesting is how QUIC defends against reflection attacks. And to explain what a reflection attack is, it's instructive to look at the QUIC handshake. So, and this is basically a TLS 1.3 handshake. So the handshake starts with a TLS client hello, which is a packet that is usually, depends on the keys that you're using, but it's usually like 200 or 300 bytes in size. And then the server replies with a server hello, which is also like 200, 300 bytes, and then it sends it a certificate chain. And this certificate chain can get really large. Like in practice, the certificate chain is a couple of kilobytes. So this is not a problem on TCP, because on TCP you start with a three-way handshake, right? You have the SYN, ACK. And once you've done this three-way handshake, you know that the client actually owns the IP address. But on QUIC, an attacker could just send the client hello packet and not put its own source IP address on the UDP packet, but put a victim's address there. And then the server would go and just send like kilobytes and kilobytes of data to that poor victim. So what the attacker gained from this, the attacker had to send a 200-byte packet and got like a couple of kilobytes sent to the client. So this is a great amplification and reflection attack. So QUIC has a few mechanisms to defend against this. The first defense is we are making this attack less attractive by requiring the client hello to be sent in a large packet. So even if your client hello is just 200 bytes, the QUIC specification says like your initial packet that you put the client hello in needs to be at least 1200 bytes. You have to use some kind of padding to fill the packet up. So now this attack is like not you send 200 bytes and the victim gets a few kilobytes, but at least you send 1200 bytes. We'll talk about retry packets later. They add one RTT to this handshake, so they are not, you don't want to use them in the common case. QUIC also defines an amplification limit. So the specification says a server must not send more than 3 times the amount of bytes that the client has sent. So if the client sent a 1200 byte packet, the server can only send like 3.6 kilobytes in reply. So once the client receives those packets, it will send an acknowledgement packet. This acknowledgement packet is, again, an initial packet, will also be padded to 1200 bytes again, which would give the server another 3.6 kilobytes that it can send over the wire. So this is not a desirable situation because it involves like sending this acknowledgement, which will cost 1 round trip. But at least it makes sure that the maximum amplification you can get out of any QUIC server on the internet is a factor of 3. There's some interesting research done about this from the guys at Fastly who've been very, very active in the development of the QUIC protocol. And they also have a very, very large customer base. And they can look at their TLS certificates because Fastly terminates the TLS connections of their CDN customers. So they found out that there are 8%, in 8% of the cases, their customer certificate chain is so large that it never fits within these 3,600 bytes. And they found out that in 56% of the cases, it always fits. Certificate chain is small enough. And then in the remaining 35% of the cases, if you just send them uncompressed, it wouldn't fit. But if you use a TLS 1.3 extension that compresses certificates, or at least the metadata in the certificates, you can make them fit. So one lesson learned from this is if you're running a QUIC server, it probably makes sense to measure the size of your certificate chain and to turn on certificate compression. So that's what you can do on the server side. There's also some tricks you can play on the client side. The QUIC specification says that you need to send 1200 bytes, but it doesn't prevent you from sending a larger initial packet. You could send, let's say, 1500 bytes, and then give the server another 900 bytes of wiggle room to send the certificate. However, the internet is a hostile place to large packets. And the larger a packet gets, the higher the probability that this packet is getting dropped. The 1200 bytes was chosen because any IPv6 enabled network needs to support packets of that size. So it's basically guaranteed that if you can do IPv6, then you can also do 1200 byte QUIC packets. 1500 bytes will probably never go through. So there is a sweet spot between those 1200 bytes minimum and these 1500 bytes maximum packet size. And Google has done some measurements. They found out that sending a packet that has 1280 bytes apparently is the sweet spot, and you get really good success rates. So this is what Google Chrome would do, and what the QUIC implementation that I've been working on also does. Another more aggressive thing that you could do, and I'm not recommending to do this, but you could send the first initial packet and then immediately send another one, a copy of that packet. This would give you two things. First of all, if one of those packets is lost, doesn't matter, your handshake can still continue. And it would give the server twice as much space within the amplification limit. However, it puts a lot of load on the network, so unless you're really sure that I know that the server I'm connecting to will have a huge certificate chain, you should probably not do that. I already mentioned that there's a retry mechanism which adds one round trip to the handshake. And this mechanism was designed for servers to defend against resource exhaustion attacks. So again, on QUIC, we have the problem that with just the first packet of a connection, and we know nothing about the client at this point, we already start the TLS handshake. And cryptography is quite expensive. When you receive the client hello, you need to generate keys and do crypto to unpack this packet, to pack your response. So it's really easy to flood a server with just a bunch of initial packets and have it do expensive crypto, and then you just throw away the response. So we need to have a defense against this. The defense is the retry packet, the retry mechanism. When a QUIC server detects that it's under load, it can send this retry packet, which basically means, okay, I received your initial packet. I know that you want to establish a connection with me, but I don't trust you at this moment. I sent you this retry packet, which has a retry token in it. And please come back to me with your same initial packet that you had, but put this token on the packet. And thereby prove that you own this address and that you're really committed to creating this connection. So this way, a server can, like, in like normal operation mode, you would never send this retry packet. You just accept everything a client sent you, and you do the one RTT handshake. But when you detect that something fishy is going on and my CPU load is going up and I'm seeing a lot of failed QUIC connections, then you activate the retry and make every client come back with this retry token, and handshakes take 2 round trips then. So this is nice, this works, but we put a lot of thought into the design of this retry mechanism. Because one lesson that was learned from TCP is that you don't want the network to meddle with your connections. So TCP is very old, right? It was invented in the 70s. There's nothing encrypted in a TCP packet. Every field can be read by anybody who touches the TCP packet. And the sad thing is that a lot of routers and middle boxes that handle TCP actually read these packets, and then they try to optimize stuff. And in some cases, this works fine. But when you want to evolve a protocol, this really hurts you. There's a TCP fast open RFC. It's been around for a long time. It would allow a 0 RTT TCP handshake. It basically cannot be deployed. The same goes for TCP multipath, which allows you to send packets along multiple network paths for the same TCP connection. It's also very difficult to deploy this on live networks because there are so many routers and middle boxes on the way that try to read the TCP packet. Of course, they don't understand these new extensions yet. They just assume that this is like the TCP that they've known for the last 2 decades. And then they try to optimize stuff. And this just breaks TCP connections in very unpredictable ways. So what we said when we were designing QUIC is we don't want any involvement of the middle boxes. They should forward the packet, but they should not be able to gain any more insight from looking at a QUIC packet. Of course, one exception to that is connection IDs. They need to be open, they need to be in the clear, so our load balancer can read them and route our packets. But everything else in the packet, we encrypt. So the question was, when we designed the retry mechanism, how do we make sure that your network provider doesn't say like, no, I don't trust you, I'll send a retry packet now. And then it would just drop the packet before it even arrives at the destination server. And then you could imagine a situation where your mobile network does this, where the next network that the packet passes through does this, and the server does it again, and then you add like five round trips before establishing a connection. We didn't want to end up in a situation like that. So what the design says now is like we have the destination and the source connection ID in the retry packet as well. And when you send a retry packet, you have to change the connection ID. And then during the TLS handshake, you have to tell your peer, like, this was the original connection ID. So the way that this works, because retries are supposed to be stateless, is that a server would generate a retry token, and the retry token contains the original connection ID in an encrypted way. Then you send this retry token back to the client. The client echoes the retry token. You get it, you decrypt it, extract the original connection ID, and then you put this original connection ID back into the TLS handshake, thereby proving to the client that it was you who sent the retry packet. So nobody else on the network other than the infrastructure of the server, anybody who has access to the keys of the server can actually perform this retry. Next thing I would like to talk about is stateless resets. Stateless resets are kind of like TCP resets, but a lot cooler. And we are continuing the theme here. We don't want any middle boxes to interfere with our connection. So in TCP, there's a reset packet. And when you receive a reset packet, your connection is dead. And because in TCP, nothing is authenticated, any middle box can just send you a reset, and then your connection is dead. In fact, this is how a lot of firewalls work. That would kill your TCP connection by just sending you a reset. So we don't want this in QUIC. A reset needs to be authenticated and encrypted. So, but what happens now when a QUIC server crashes? Let's say we have a server in behind a load balancer, and the server goes down. Something unexpected happened, or maybe it's due for upgrades, and the server is gone. So one thing that you could imagine would happen is, well, nobody has the keys anymore. The client keeps sending data, and it doesn't get a response. So at some point, it will run into a timeout. But this is bad. Like timeouts take time. It's like 10 seconds, 20 seconds, 30 seconds, depending on how you configure this. But this is definitely noticeable to the user if your connection breaks due to a timeout. So we don't want that. So that's why QUIC came up with an explicit signal, which is the stateless reset. The idea behind this is to make this reset packet look on the wire exactly like a normal short header packet. So this is the short header that I showed you a few slides before. And one thing I didn't mention back then is that every QUIC packet has an authentication tag, the purple thing at the end. This is because we're doing cryptography, we are encrypting a message, and we need an authentication tag, right? So the idea behind the stateless reset is to have some magic values for this authentication tag. And if the authentication tag matches this magic value, then it's not then the node knows it is not a normal packet, but it's a reset packet. And because this authentication tag is 16 bytes long, it doesn't. There's basically no chance of like a normal packet being misidentified as a stateless reset. Like the collision probability is just so low that we don't have to care about this. So how exactly does this work? Like having one global value obviously doesn't work. Then everybody would just look in the spec and see like this is the magic value. We can't do that. We can. What also doesn't work is if you have like one load balancer set up that defines like, okay, our magic value is X. Because then I just go to the load balancer with an unknown connection ID, get the stateless reset packet and read this magic value and then use it to attack other people and tear down their connections. So instead what QUIC is doing is it is coupling the stateless reset token to a connection ID. And every time I give my peer a new connection ID, I don't only give them the connection ID, but I also give them a stateless reset token associated with this connection ID. So it's always these two values that I give my peer when I give them a new connection ID. Okay, but now you might say the server just crashed. How does the server now know that this connection ID was associated with this magic value? So here, cryptography will help us. And this, I find this really cool. So every server setup needs to have some long-term private key, right? This is just for doing TLS. You need to have the private key associated with your TLS certificate. And this will be stored in some way that it doesn't get lost when the server crashes. So what if you just apply like a function that takes a private key and a connection ID, it could be a hash function, for example, and derives a stateless reset token from that function. Now when the server receives a packet with a connection ID that it doesn't know, it just applies this function and it derives this magic value and sends it to the client. And the client will recognize this, okay, the server has crashed, this connection is dead immediately, and I can immediately redial a new connection. There's an interesting caveat here. Imagine that both sides go down at the same time. They will keep sending each other stateless resets till the end of time, right? So how do we solve that? So the rule is that you can only send a stateless reset packet that is smaller than the packet that you received. So the things that are constant in the packet is you have the 16-byte authentication tag, and you have some space for the connection ID. And between this is all application payload. So as long as you decrease the size of this fake application payload that you're sending, at some point the packet will get small enough that you can't fit an authentication tag into the packet anymore. And this ping pong will die down. It may take a couple of hundred packets, but then this is kind of an esoteric situation to begin with. So we don't really care. So this brings me to the end of my talk. Quick overview what's going on at the IETF at the moment. We are defining a QUIC version 2, which is exactly the same as QUIC version 1. Why are we doing that? You've seen before that in the long header packet, there's this version field, like the 32 bits where we just put a single 1 in there. And what we want to prevent from happening is that the network operators get used to this field having the same value every single time for every QUIC packet that they see. Because if people learn that we can identify a QUIC packet by just looking at the version field, and the version field will always have the value 1, and we then just block everything else on the network because it's certainly not QUIC, right? That would be a bad situation. We want to be able to use this version field and put different version numbers and eventually end up with 4 billion QUIC versions. So this is the first step, to just define a QUIC version that will, on the wire, will have a 2 in that field. And will, from the internal workings, you don't need to change anything in your QUIC stack. You can just process it as if it was a QUIC version 1 packet. And then next year or the year after, or who knows, we will hopefully have QUIC versions that actually add new features to QUIC. The second pretty exciting development is a protocol called MASK. And I guess I have to say this now, that we came up with this name before COVID hit. And it has this very smooth name, multiplexed application substrate over QUIC encryption, and I have to look this up every single time. What this protocol does, it's a proxying protocol over QUIC. In HTTP, you have a connect protocol when you're running on top of TCP, which basically tells the server to proxy a TCP connection to another endpoint. And we wanted to have something similar, but based on QUIC, to proxy UDP packets, and this is exactly what the MASK protocol is used for. And then the third development that I won't talk about a lot here is web transport. I will talk about this in my second talk today. It's basically, think of it as WebSockets but run over QUIC. So that's it from me. Thanks for attending the talk. My QUIC implementation is here. It's QUIC Go, and it's used by lib-P2P. And we are also working on QUIC support in the Rust implementation. So if you're interested in this, please get involved.
Thank you very much. Guys, questions? Okay, there.
Thank you. So I'm a little bit puzzled. You started the talk by saying QUIC is much better than TCP in every single way. Then in slide number 7, you present the reflection attack that could not happen in TCP, but you tried to mitigate establishing this kind of cap on the amplification. Then on slide number 9, you present how easy it is to DOS a server because you have to do this crypto thing, and then you present this token in order to solve this. So it does look to me like there is a bunch of new attack vectors that come up with this new protocol. So I would like to know, what are your thoughts on this?
So you mean, is this really better than TCP if we have these new attack vectors? Yeah, I mean, I was talking more from a performance perspective. Like from the performance, you have a faster handshake, you have better loss recovery, you have better congestion control available. So in that sense, it is better. To get to these benefits, we had to like cut round trips and do like all the stuff that I presented here to make it work, which then creates new problems. But I believe that the mitigations that the QUIC protocol has built in make it such that these attack vectors are not very attractive anymore, and that you can actually safely run QUIC in production.
Anybody else? Curious? Okay.
Hi, thanks for the talk. It was great. I'm just curious. Do you have any idea what's the fraction of traffic in the internet nowadays that is QUIC?
I don't have the current numbers, but I would expect it to be pretty high, because a lot of the traffic, just like looking at raw bytes transferred, is done by YouTube. It's done by Facebook and by Netflix. Okay, I'm not sure if Netflix uses QUIC by now, but at least YouTube is on QUIC, and Facebook is on QUIC, Instagram is on QUIC. So a lot of the largest websites in the world are using QUIC. So it would be a significant amount of traffic.
Okay, great. Number 3. You have just 2 questions? Okay.
Great talk. I really like the mitigation, the problem statement and the mitigation strategies. With the stateless reset, how does the client know that the token is valid? Because the client doesn't know the private key of the server, right? So what's to stop some middle box from just creating a token there?
The server told the token to the client before. When the server told the token, this is a connection ID that you can use to get through my load balancing infrastructure, it also told me, told the client the magic value associated with this connection ID is the following.
Got it, got it. Okay, thanks.
Great. So
any more questions?
Okay. I think that's about it. Well, thank you again. Very interesting.